it over to Arun. Can you share your screen?
Can you guys hear me?
Yes, we can hear you. Can you share your screen?
Yes, give me a moment. Yes, is the screen visible?
Yes, it is. So yeah. Go ahead.
Yeah, thank you. Hello all, good morning to the people in India and good evening to the people in the US. My name is Arun Kumar Karangala. I'm a postdoctoral candidate at Texas A&M. I work with Dr. Charan Singh, mainly on reliability assessment of distribution systems. And with UI Assist, I'm working on Theme 6, Objective 2.7.8, Reliability Assessment and Improvement. I'm going to talk about the novel reliability assessment framework for the evolving distribution systems. To start off with, let us go with the power system networks introduction. Now, as you all know, electric grid is divided into three main functional zones: the generation, transmission, and the distribution system. This work is focused on the distribution system of the electricity grid. Now, the demand in the US is categorized by different sectors. Now, residential systems account for about 38% of the US demand, and of which single-family detached homes consume about 74%. And the commercial electricity consumption accounts for about 36%, of which there are four types of buildings: office, mercantile, education, and healthcare account for about more than 50%. Now, industrial electricity consumption accounts for about 26%. And more than 75% of the US electricity demand is supplied through the distribution system, which makes it a very critical system for reliability. To that end, let us look at the definition of the distribution system and its evolution over the course of time. Now, distribution system is defined as the portion of the power system that delivers electric energy from the transmission points on the transmission system to the customer. It is generally considered to be anything between the distribution substation and the customer meter. So traditional distribution systems are unidirectional, static, and radial systems, and power flows from the network to the customers connected to the network. Now, with the adoption of renewable energy generation, it became a primary driver in the evolution of the distribution system. And with the emergence of DERs, it enabled DERs to be connected at the feeder level. Now, power flow is still unidirectional here from the network to the customer, but with additional components added to the distribution system from a reliability perspective. Now, with DER technology becoming cheaper, these are being connected both at the feeder level and the customer level. Now, these systems evolved from being unidirectional, static, and radial systems to bidirectional, dynamic, and somewhat meshed systems. Now, within these systems, with higher penetration, there are DGs and energy storage and EVs installed behind the meter at the residential systems. At the commercial systems and at the industrial systems, we have DGs and energy storage installed behind the meter. Now, let us come to the context of reliability, like what is reliability in the context of distribution systems. Before going there, let us define reliability in a power systems. Now, power system reliability is concerned with the ability of the system to satisfy the load on the system while operating the system in a manner that respects the capabilities of generation, transmission, and the distribution components. Now, there are several measures to indicate underlying probability, but most of the times we use power system reliability indices to measure the reliability of the system. Now, due to the size and complexity of the power systems, reliability evaluation of an entire power system is never evaluated, but a set of sequential studies are performed, like generation system adequacy studies, transmission system studies, and distribution system studies. Now, consider this system with 4 load points, a distribution system with 4 load points. Now, power flows from the network to the customers through the system elements and the distribution transformer. Failure of any element between the supply point and the load, between the supply point, okay, just give me a moment, sorry. Yeah, between the supply point and the load point will affect the customer. Now, consider a failure of a main section in the main feeder. A circuit breaker operates and disconnects the entire feeder. Once the line is disconnected, the circuit breaker is again opened, and then the power is only supplied to the load point 1 of the distribution system. Now this constitutes a stage 1 distribution system. Now let us assume a stage 2 distribution system where there is alternative supply and the rest of the system is also supplied through that alternative power. Now, the important point to notice here is the fact that if there is no power available at the load point, then the customers are interrupted. Now, therefore, system indices can be evaluated using the load point indices. Now, the load point indices are failure rate lambda, repair rate or repair time R, and unavailability U, and the system indices can be used by the formulations here. Let us look at the same system earlier, but with DERs connected behind the meter, indicated with the blue squares behind the load points. Now, here power flow happens from the network to the customer. An assumption here is that the DERs are able to supply the full load of the customer. Now, there could be a failure in the DR system similar to the one that we have seen earlier. Now, if there is a failure in the lateral feeder here, what happens is the load point connected to that feeder experiences an interruption, and the customers without DER connected to the failed feeder will experience an interruption. Now, the important point to note here is that even though the load point experiences a failure, all the customers connected to the load point are not interrupted because the DER installed behind the meter will take care of the customer's load. Now let us look at this reliability context by a numerical example. Now consider the simple system with two load points. The load point data shows that there are like 20 customers in total, with 10 customers connected to each load point. Now let us evaluate this system average interruption frequency index from the basic definition, which is the sum of total customer interruptions over the total number of customers. Now in case 1, the system is assumed to be a traditional system with no DERs installed behind the meter. Now each customer is interrupted only when the load point is interrupted. Therefore, the failure of customer is equal to the failure of the load point. Now when we do the math, it comes down to the formulation used using the load point indices. Now consider the same system in case 2, where the customers are having behind the meter DER. Now the assumption is that the DERs are perfectly reliable and the supply power whenever there is a failure. And another assumption is that half of the customers have DERs and half of the customers do not have DERs. Now, while using the index definition to calculate system average frequency interruption index, we can see that only half the customers will ever experience a failure when the system fails, and the other half will always be supplied by DER irrespective of the system condition. Now, in this case, load point reliability indices cannot be used to evaluate the system indices. While the example assumes simplistic scenarios, it proves that the fundamental approach to use the load point reliability indices does not work with behind the meter DERs. Now, to that end, we propose a framework, a 3-level hierarchical framework, like the reliability assessment of the bulk power system. The 3 levels are divided based on the complexity of modeling, objective of analysis, and authority of control over the equipment and components installed. Now, these 3 levels include various aspects of the modern distribution systems. Now, in level 1 evaluation, DERs at the feeder level are considered, and we evaluate the primary load point indices. Now, there are numerous methods to evaluate primary load points indices in the literature. The base level of reliability is provided by the distributed system operator, whereas the DG and the energy storage systems connected to the system level will boost the reliability of the load points. Now, level 2 evaluation builds upon the primary load point indices evaluated in level 1. This level considers behind the meter installations of the customer and their effect on the system reliability. Now, in level 3, we consider coordination of resources in the system, optimal operation of DERs, cyber-physical systems that enable communication, and control strategies. So this work is heavily focused on level 2 assessment and a part of the level 3 assessment of the distribution system. Now, the method to evaluate the level 2 system of the indices of the system, I'm sorry. Now, as mentioned earlier, we use load point reliability indices from level 1 as input and include the effect of having DERs behind the meter to evaluate system indices. But how do we achieve that? We achieve that by evaluating the equivalent load of the customer. Now, what is equivalent load? It is the demand seen by the system from a customer after considering behind the meter DERs. Now it is very simple to evaluate. The green curve here is the hourly load curve, and the red curve is the equivalent load curve, which is obtained by subtracting the energy supplied by the on-site DG. Now, the equivalent load captures stochastic nature, variability, and availability of the DG and the ES systems. So we have the equivalent load. So how do we calculate the system indices? Now we must go through each customer and evaluate the interruption indices for each customer, and it is done using Monte Carlo simulations. Now we create artificial load point operating history using the basic load point reliability indices. We calculate the uptime and downtime using the reliability indices, assuming that the failures are exponentially distributed. Now then we look at the equivalent load and look at when the DGs are not able to supply in case there is a load point failure. And then we calculate the average interruption frequency and average interruption duration using the interruption duration and interruption times. In the current literature, the fundamental approach to evaluate system indices is to evaluate the load point indices and then use them to evaluate the system indices. Now, in the newer approach that we propose, once we evaluate the interruption indices for each customer, we can evaluate system indices using the formulations developed here. Now, SAIFI, as seen earlier, was total number of customers interruptions over the total number of customers connected. Now, in this new formulation, where A is a set of customers with behind the meter DERs, each customer average interruption frequency is evaluated and then summed up with the customers without any DER. Now, the problem now boils down to calculating the equivalent load of the customer. When we consider the modern distribution systems, not all customers have behind the meter DER. We can intuitively categorize them into three types based on the DER installed behind the meter. Type 1 without any DER, type 2 with DER with only distributed generation, and type 3 with distributed generation and energy storage. Now, the widely used DER behind the meter is the PV system, and to that end, we developed a reliability model to calculate the equivalent load of the customer with PV systems. Now, PV systems employed on the rooftops have solar panels and inverters as main components, and microinverter configuration is used in this study. Now this module is called as an AC module. Now, the AC module subsystem is modeled as a single unit with two states, but a typical customer with behind the meter PV system will have multiple AC modules connected to form the PV system as a whole. A PV system is generating system, and usually generating systems are modeled as 2-state or 3-state systems with additional state for derated operation. Here, we model the PV system as a multi-state unit. For N module PV system, we model it as an N+1 state, including the zero capacity state. Now, from the state transition diagram, we can calculate the power output. We can calculate the probability of the system in a particular state to go from state I to state I+1 or I-1. And we can also calculate the residence time in each state. Now, similar model for the energy storage is also developed for type 3 customers, where the state of charge at each time step is evaluated. Now, these models are applied to a Roy-Billington test system for the bus 4, which is a distributed it is a distribution test system with 38 load points and 4,779 customers. This system is assumed to be in a location in Phoenix, Arizona, and out of the 4,779 customers, 4,700 are the residential type customers. Now, from the analysis, the residential customers are assumed to be of different mix. Now, we have 4 cases of analysis. Now, the results show that there is an improvement in the estimation of reliability indices with level 2 assessment. Mix 2 and Mix 1 have similar reliability indices, but Mix 3 and Mix 4 with higher penetration of DG and ES have much higher level of reliability indices, as in lower number but higher level of reliability. And we can also see that as the rated capacity ratio or the nameplate capacity ratio installed on behind the meter increases, the change in SAIFI decreases, but overall reliability index increases. We also proposed a test case. Sorry for that. Just give me a moment. Yeah, we also proposed a use case for the developed framework. We have analyzed the top 100 most populous counties of the US, where 46% of the US population resides, and then We assume that the grid characteristics remain constant toward the country, and so the grid adds no additional value in terms of reliability. But the DERs behind the meter will add a reliability value depending on the geolocation and the parameters of the system. Now, from these analysis, the inferences that we got out where the system reliability increases with increase in installed DER capacity, irrespective of the location of the system. Now, area of interest for the DER sizing to achieve optimal reliability rise within the rated capacity ratio of PV between 0.5 and 2.5. And within this range, the rated capacity ratio of energy storage as much high as possible will give the better reliability of the system. And system reliability depends on the climate zone, that is load behavior of the system. And in each climate zone with similar load behavior, reliability depends on the global horizontal irradiation of the location, that is the amount of sunlight that falls on the panels. And in each climate zone with variable load behavior of the system, reliability of the system depends on the load factor. Systems with lower load factor perform better than the systems with higher load factor when the DER is sized based on the RCR metric. Coming to the conclusion, we have proposed a 3-level hierarchical framework which clearly defines the roles of the DSO and the customers. And we developed a level 2 assessment that quantifies the contribution of the customer. We generalized a methodology for the level 2 assessment and proposed a methodology that can be used with any DG if it can be modeled as a source with hourly power output. And the proposed methodology also provides a higher granularity by factoring in the impact of customer level components in the distribution system reliability. And we also demonstrated the use case for the developed framework. All of this has been submitted and accepted into a journal, and we have also submitted a paper to the IEEE Access recently with the use case. And the future work is to evaluate the energy-based indices and do a bunch of sensitivity analysis. And the major work going forward is to integrate the demand response in the reliability evaluation of the system. So I think that is it. And yeah, we are open for collaborations and questions.
Great, thank you, Arun. So the first question is, how do you get information for customers and how often?
So that's a really good question. We don't really get, as in this analysis, we are considering values, like arbitrary values or the existing values for the customers. And the problem with the existing methods are we don't really get the installed capacity of customers behind the meter. So that is one thing that needs to be done for our method to be like validated. I hope that answers the question.
Yeah, there's a second question, and if there's follow-up, please feel free to add. Can you please tell how the load factor plays in the role of reliability?
Yeah, so the load factor, when we consider load factor, the systems with usually the DER systems are installed based on the peak load of the customer. So when we consider the peak load, when the load factor to be high, then the system installed behind the meter will be adequate enough to supply the reliability or supply the power in a more reliable fashion. But when the system reliability, like when the DER installed behind the meter has higher load factor, or the customer has higher load, lower load factor, which means that the peak load is much higher than the average load, then the DER installed behind the meter has higher capacity, which leaves out that the DER installed is not efficiently being used. So in that case, when we have higher rated capacity of DER, it has higher reliability. So that is one of the anomalies that we found using the, like when we did the use case for the analysis. Yes.
All right, the next question is, how does the level 3 parameters like control and cyber part from DERs, how is it taken into account for this study?
Yeah, right now we are trying to integrate demand response, and the next work we haven't gone to that part yet, but the next work is trying to integrate control strategies and cyber part from the DERs.
Okay, so that'll be next year's workshop. You can talk about that.
Yes.
Okay, here's another follow-up from the earlier question. How often do you need customer information data? And do you think behind the meter estimation will help with this reliability computation?
So when we are talking about reliability computation, this is not an operational computation, but this is a planning study. So we would need reliability. What we would need customer information. Maybe it depends on the DSO. If they want to do planning studies every year, then we might need customer information yearly, the installed capacity or the added capacity of the DER. So yes, behind the meter estimation will help with this. If that is the case, we can also do a rolling operational reliability evaluation, and that can also help elevating the peak ramps as the earlier presenter told. We can use that to evaluate the reliability constraints as well. Yes.
Okay, we have time for one more question. Any other questions? So Arun, if you want to, can you go back to your map and your PowerPoint?
Just give me a moment. Okay.
The map you have of the, yeah, of the US.
Yes.
Do you have the map of the US where you had the different?
Yeah.
Yeah, so how do you see this reliability information impacting how we would do different activities in different parts of the US? How do you see this information being used as we might have regional strategies related to the DERs across the US?
Yeah, so one thing that we found here is that with in especially in the lower like the southwest part of the US where the solar panels are like where the GHI is higher, system reliability is very high when we use the DER comparable to the peak load of the system, and the load factor here is very less. So when we consider systems like or places like Houston or Dallas, which are hot and humid, there the strategies have to be very different than how we deploy or control DERs from Southwest. And say in New England area, there is ample sunlight, but we need higher rating DER behind the meter to achieve the same level of reliability. So the one thing that I can tell you right now is that to achieve the same level of reliability, the installed capacity in the Southwest should be lesser, and the installed capacity in Northeastern is much higher. So installed capacity will change, and the control strategy is going to change.
Okay, so one size doesn't fit all.
Yes, yeah.
So last question would be, will you consider dynamic studies?
No, we don't really consider dynamic studies. It's just a planning study, so we are not looking at dynamic studies.
Great. Well, if you might want to put your email in the chat, and then we're going to head on to our next presentation. Thank you very much, Arun.
Yep. Thank you all.
Okay, so we're going to head into our third talk, which Shirashi is going to present from Washington State University. So Shirashi.